Hello, and welcome to Wallace's Mysteries of Antiquity. Subscribe to the channel to join me in exploring the enigmas of our distant ancestors and try to come to tentative conclusions about them. Whenever I'm able, I like to use my skill set to do original science, as I'm uniquely qualified in the archaeology YouTuber space to do certain types of analyses. I'm just a layman with Egyptology, but in mathematics and engineering, I can bring a senior professional level of expertise to the table. History for Granite's Revenge of the Bent Pyramid video had a line in it that triggered the engineer in me to just start doing some math.
Nerd!
YouTubers don't have the luxury of getting peer-reviewed before publishing. Our viewers are our peer review. To be honest, there's a level of anxiety for the first few hours after hitting publish, wondering if I'd made any glaring errors. He's kindly pointed out mistakes I've made, and I've done the same. I hope he doesn't get tired of me. But he mentioned something that turned out to be not quite correct, and I thought the research would make a great video. So I'd like to put forward my new research to correct his statements, actually strengthen his narrative, and quantify something that can seem very abstract. How good are the various corbellings? Because the amount of overhang by itself doesn't really tell you anything. He credits Peter James to a claim that the corbels in the upper chamber of the Bent Pyramid and Meidum pyramids are too aggressive, especially compared to the red one. There is a single source provided with that author, and it does not mention the corbels. Nor can I find it in any of his other works. Perhaps he misattributed someone else's claim, but I couldn't figure out who. History for Granite is a skilled researcher, so I think we can assume that he did read it from somewhere, and it still likely was Mr. James. I wanted to peer review the source, because even a visual inspection gives me the impression that the red ones are no better than the bent ones, and I wanted to know how they came up with their conclusion. Was this a back-of-the-napkin calculation or a rigorous analysis? I have a suspicion of what they did and why it's wrong, but without a paper, I can't check their math. Luckily, we don't really need that paper. I'm perfectly capable of doing that rigorous analysis myself, so I devised a formula to score the different ceilings. If the science is sound, then it should be repeatable, and even different analysis types should agree with each other. If we disagree, well, my source code and data is available in the description, and I welcome the peer review. I actually went through most of the corbel ceilings of Old Kingdom pyramids, and produced a score for each one, so we can see if they were trending towards or away from correct ceilings. Let me first explain what I even mean by a correct ceiling. In a perfectly shaped ceiling, all of the pieces collectively have minimal forces on them, both vertically and horizontally, since you are redistributing forces. You probably already know that an arch is stronger than straight corbelling. This was common understanding by Greco-Roman times, but the truly ideal shape eluded engineers until Leibniz, Huygens, and Bernoulli were able to derive it mathematically in 1691. However, the shape was discovered in the early 1600s, as you can approximate this function in an analog way. If you take all of the forces involved here and reverse them, you change from a compressive force to tension, but the numbers don't change. This is the same formula that predicts how a chain will hang, allowing you to trace it upside down. Check out this video for a deep dive on that subject. In fact, many of the most complicated ceilings were created after this realization, and allowed architects to make arches that interact with each other in unbelievably intricate ways. Check out the ceiling of the Sagrada Familia on the left. This was modeled upside down, and is still standing. So we do know exactly what shape a ceiling needs to be to ideally distribute its load. It may look like a parabola, but it's actually a hypercosine, specifically this formulation, called a catenary curve. The a variable is a scalar, which is a function of the length of the chain. Since I want to specify height and width, I created a function to calculate A for me. I could integrate the differential, but because I know the approximate range, I just brute force it until I find the closest millionth using a binary search. To mark the location that I want to analyze, I place a pure green pixel on the inner corner of each corbel in a diagram. This tells the software where each anchor is and the slope to the next stone. A lot of the drawings are diagrams by John Paring, a talented draftsman. There will obviously be some error inherent in that, but I checked them and they're pretty close, plus I slightly stretched them to be more correct, within a reasonable error for my purposes. Some other diagrams were just generated from actual measurements. I calculate the ideal catenary from the first location, then move up one and see how far the actual next location deviates left or right from the ideal. If the next stone is outside of the arch, then there is no structural problem, but it is shallower than it needs to be and will get tinted blue. For example, the stone on the top left here can ideally overhang 520% more than it actually does. If the next stone is inside of the ideal curve, then the step is too aggressive, and it is under unnecessary stress. This stress will tint the block red in my output. For example, the bottom left block is sticking out 46% too much. I used a distance along the x-axis to determine error. You may think I need to use the curve's derivative and a dot product to get the closest point to the curve, but that's not actually the case because we assume the y level of our course is fixed because we're talking about physical stones. So the horizontal plane is the only axis of movement. You can see this corbel should have about half as much overhang as it actually does. Then we move up and repeat. There is the potential to make a mistake here, and perhaps Mr. James did. The ideal curve from the second block is a continuation of the previous curve if and only if the current block is perfectly placed. Otherwise, you are starting a new curve on a new foundation. Each block needs its own ideal curve calculated. This is why my program shows a new curve for each stone. Here is what a perfectly corbelled ceiling should look like. All the blocks are perfect magenta, and each corner exactly matches the curve. The minor error being shown at the top is from the flattening curve adding noise, but the corbel is mathematically perfect. Here's a corbelling that's both too aggressive and one that's too shallow, as well as ceilings that lean left or right. The bottom two blocks will always be perfect magenta for reference. These blocks are sitting on the ground, so by definition they aren't overhanging anything. Keep this in mind, it will help you look for subtle differences. I chose this color scheme because everyone should be able to see it, even those who are colorblind. Those of you with a keen mind for math might realize that if you use a good consistent slope for the corbelling, it'll start too aggressive, like you see, and end up too shallow, intersecting the curve near the top. An ideal straight corbel will still have an average error of 0. Not perfect, but certainly good enough for the Egyptians' purposes. There is a limit to how high you can push that error before it structurally fails, but we don't know what that failure point is. Other factors like weight, moisture, and stone quality affect that. To determine if the aggressive corbelling played a role in the destruction of said corbels, we need to compare their error value to other pyramids that we know did not collapse. We should be able to get a Boolean yes or no, were the corbels in the bent pyramid any worse than any other pyramid, and specifically the red one. Well, let's go through the ceilings in the order that I believe them most likely constructed, starting with the upper chamber of the Meidum pyramid. It has an average error score of 60% too aggressive. In Mastaba 17, also at Meidum, we see an average error of 15% too aggressive. You can see a pattern that these constant slope ceilings are far from ideal and have a lot of extra stress at the bottom. This one was probably designed with a less steep ceiling because it only needs to support a mastaba above it, not a full pyramid. Though they're certainly starting off in Meidum with plenty of room to improve. In the bent pyramid's lower chamber, we get two different scores because the ceiling is corbelled in both axes. From east to west, the shorter direction, the corbels are way too aggressive. But in the other direction, the ceiling is actually quite good. This is the lowest levels of stress we see so far, actually averaging out to too shallow. Above the portcullis, we see an interesting corbel that is somewhat respectable. The left side is taking more stress, but the right is very close to neutral magenta. The upper chamber is also corbelled in both directions, and although the north-south corbelling is far too aggressive again, in the other direction, we have a number of stones shallower than necessary, just like the lower section. Several of the ceiling stones that show great damage are in these very relaxed corbels, so it seems unlikely that the corbel design caused any damage. Now the moment of truth. How are the corbels in the red pyramid? Awful. These are much worse. You can clearly see every stone is heavily red, even up high with the exception of the very top stone. Remember, the bottom two stones are colored neutral. When comparing the best corbels of the red pyramid on the left to the worst corbels of the bent pyramid on the right, we see very little difference, and the red pyramid doesn't have the luxury of the better corbelling in the other direction. I think I can conclusively say that the bent pyramid's corbelling is not worse than the red pyramid's. If anything, the extra direction with a pretty good curve makes it much better. I don't think we can blame the current condition of the bent pyramid ceiling on the corbel design. For the bent pyramid satellite, it gets a little better, but shows a very similar stress pattern to the smaller chambers of Meidum, so they don't seem to be advancing in knowledge much. However, for the Grand Gallery of the Great Pyramid, they chose a much better shape. Perhaps this was in response to damage already in Snefru's ceilings, or maybe it was dumb luck. A utilitarian use of the Grand Gallery may also explain the different shape. I did both the top and the bottom of the Grand Gallery, and they were basically the same. Still starting off too aggressive, but better, and taking a steeper angle means that by the top, the stones could have been pushed 5 to 10 times further. So in conclusion, neither History for Granted nor I believe this pyramid to be a failure, and that Egyptologists are suffering a cognitive bias because they've convinced themselves that it was. The corbelling in the bent pyramid is demonstrably more sound than those of the red pyramid, so in the same conditions, it should have held. This strengthens our claim that the bent pyramid is not a failure or poorly designed. I showed in my own bent pyramid video evidence for 3 phases on the ceiling, and I concluded that this destruction was likely the result of human work, not stresses from physics. In fact, I theorize this is actually the shape they were attempting to carve. Doesn't this seem logical? This is Snefru's crown, and it had the same shape since pre-dynastic times. I think they were trying to give his tomb a crown. I've created a GitHub account for this channel, and have uploaded the C++ to it for review. I plan on uploading my other tools after I clean the code a little bit. Thank you for listening. Post your own thoughts and tell me what you thought of my analysis in the comments, and subscribe if you wish to continue to explore the enigmas of our distant ancestors with me.